Tonight, we're going to shatter an image that's been stuck in your head since childhood. That neat, tidy diagram of the solar system you've seen 1,000 times. The one with the planets lined up in a row and a little ring of debris past Neptune. That diagram is lying to you. Because the Kuiper Belt, that region beyond Neptune, is not a narrow band of icy rocks. It is a colossal structure so vast, so unimaginably wide, that the entire inner solar system, everything from Mercury to Mars, every planet you've ever learned about in school, would vanish inside it like a grain of sand dropped into an ocean. And the strangest part is just how empty it is. By the end of tonight, you will never look at the outer solar system the same way again. Before we go any further, if you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've seen 100 times, maybe 1,000 times. You've seen it on classroom walls, in textbooks, on websites, in documentaries. It's the diagram of the solar system. You know the one. The sun sits on the left, big and bright. Then there's Mercury, Venus, Earth, Mars, then a gap for the asteroid belt, then Jupiter, Saturn, Uranus, Neptune. Everything is lined up neatly in a row, roughly evenly spaced, with maybe a little extra room between the outer planets. And then past Neptune, there's sometimes a little band drawn in. A thin ring of debris labelled Kuiper Belt. It looks like a slightly wider version of the asteroid belt, a modest strip of icy material just beyond the last planet. Nothing too dramatic. Nothing that would make you stop and think twice. That image is one of the most misleading pictures in all of science education. It's not wrong in the sense that it shows the planets in the correct order. It does. Mercury really is closest to the Sun. Neptune really is the farthest planet. The Kuiper Belt really does lie beyond Neptune. All of that is accurate. But the proportions, the spacing, the scale of everything in that diagram is so catastrophically compressed that it gives you a completely false sense of what the solar system actually looks like. And nowhere is this distortion more extreme than with the Kuiper Belt. The Kuiper Belt is not a thin band of debris, it is not a modest ring just past Neptune, it is an absolutely enormous structure, a region of space so vast that it makes the familiar planetary solar system, the part with all the planets you learned about in school, look tiny by comparison. And tonight, we're going to understand why. But to do that, we need to start with distances. Real distances. Not the compressed, squished, cartoon distances from that classroom diagram, but the actual physical distances that separate objects in our solar system. Because until you understand those distances, you can't possibly appreciate what the Kuiper Belt really is. Let's begin with something you already know. The distance from Earth to the Sun. This distance is about 93 million miles. In kilometers, that's about 150 million. Astronomers use this distance so often that they gave it a special name, 1 astronomical unit, or 1 AU. It's the yardstick of the solar system. When astronomers say something is 5 AU from the Sun, they mean it's 5 times the Earth to Sun distance. 10 AU means 10 times that distance. It's a convenient shorthand because the raw numbers in miles or kilometers get unwieldy very fast. Now, 93 million miles is already a distance most people can't truly visualize. Let me try to make it concrete. If you could drive a car at highway speed, say 60 miles per hour, non-stop, 24 hours a day, 7 days a week, with no breaks for fuel or sleep or anything else, it would take you about 177 years to reach the Sun. That's more than 2 human lifetimes of continuous driving just to cover 1 AU. Light, the fastest thing in the universe, covers this distance in about 8 minutes and 20 seconds. When you look at the Sun, you're seeing it as it was over 8 minutes ago, because that's how long the light took to travel from there to here. So 1 AU is already enormous by any human standard. It's a distance that took the Apollo spacecraft, traveling at roughly 25,000 miles per hour, months to cross if they had been pointed at the sun instead of the moon. It's a distance that makes everyday measurements completely useless. You can't think about it in terms of city blocks or road trips or flights across the country. It's in a different category entirely. Now let's go farther out. Mars orbits at about 1.5 AU from the Sun. Jupiter, the first of the giant planets, orbits at about 5.2 AU. That means Jupiter is roughly 5 times farther from the Sun than Earth is. Already, that's a significant jump. The distance from the Sun to Jupiter is about 484 million miles. At highway speed, you'd need about 920 years to drive there. Saturn is about 9.5 AU from the Sun. Uranus is about 19.2 AU. And Neptune, the outermost planet, orbits at about 30 AU from the Sun. Let me pause here because 30 AU is an important number. It's where the familiar part of the solar system effectively ends and where the Kuiper Belt begins. 30 AU is about 2,790,000,000 miles from the Sun. In kilometers, that's about 4,500,000,000. That's 30 times the Earth to Sun distance. If you could somehow drive at highway speed from the Sun to Neptune, it would take you over 5,300 years. 5,300 years of non-stop driving. The Egyptian pyramids were built about 4,600 years ago. You could have started driving toward Neptune when the pyramids were being constructed, and you'd still have several more centuries of driving ahead of you before you arrived. Even light, traveling at 186,000 miles per second, takes over 4 hours to travel from the Sun to Neptune. When NASA's Voyager 2 spacecraft flew past Neptune in 1989, it had been traveling for 12 years since its launch in 1977, using gravity assist from Jupiter and Saturn to build up speed along the way. 12 years of space travel just to reach the orbit of Neptune. So the distance from the Sun to Neptune, those 30 AU, is already staggering. Most people, even people who are reasonably knowledgeable about space, don't fully grasp how far away Neptune is. It's not just a bit farther than Saturn or Uranus. It's in a completely different zone of the solar system. A frigid, dark region where sunlight is 900 times dimmer than it is on Earth. If you stood on Neptune and looked back at the Sun would appear as just a very bright star. You'd still be able to tell it apart from other stars, but it wouldn't look like the blazing disk you see from Earth. It would be a point of light. Brilliant, yes, but a point. That's how far 30 AU is. Now here's where everything changes. Here's where the diagram on the classroom wall starts to fall apart completely. Because the Kuiper Belt doesn't start at 30 AU and stretch out just a little farther, maybe to 35 or 40 AU like the diagrams seem to suggest. The main classical Kuiper Belt extends from roughly 30 AU all the way out to approximately 50 AU from the Sun. That's a radial width of about 20 AU. Let me say that again because it's critical. The Kuiper Belt's main classical region spans about 20 AU in radial distance. 20 astronomical units. That's 20 times the distance from Earth to the Sun. The width of the Kuiper Belt alone is roughly 2/3 the entire distance from the Sun to Neptune. If you place the Sun at one end and Neptune at the other, covering 30 AU, the Kuiper Belt's classical extent would stretch another 20 AU beyond that. The belt's width is comparable to the distance from the Sun all the way out past Uranus. Think about what this means. Everything you think of as the solar system, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, all of that fits within 30 AU. The Kuiper Belt extends that by another 20 AU just in its classical region. In other words, the Kuiper Belt is not an afterthought. It's not a footnote at the edge of the solar system. It is a structure whose radial span is on the same order as the entire planetary solar system itself. If the planetary region is the town you live in, the Kuiper Belt is not a fence around the edge. It's another town, nearly as wide, sitting just beyond yours. and 20 AU is just the classical belt. When you include the broader Kuiper Belt region, the scattered objects, the detached populations, the objects in various orbital resonances with Neptune, the effective extent of Kuiper Belt objects reaches even farther. Some objects associated with the outer edges of the Kuiper Belt population have orbits that carry them well beyond 100 AU. But even sticking with just the classical belt, from 30 to 50 AU, we're already talking about a region that dwarfs what most people imagine. Let's convert this to real distances to make it tangible. 20 AU is about 1,860,000,000 miles. In kilometers, that's roughly 3 billion. If you were to drive across the width of the Kuiper Belt at highway speed, 60 miles per hour, it would take you about 3,500 years. The fall of the Roman Empire happened about 1,500 years ago. You'd need to have started driving more than 2,000 years before Rome fell, just to cross the width of this one region of the solar system. Light takes about 2 hours and 46 minutes to cross 20 AU. Sound, if it could travel through space, which it can't, would take roughly 250,000 years. Let me try another comparison. The distance from Earth to Mars at its closest approach is about 34 million miles. The width of the Kuiper Belt, 20 AU, is about 55 times that distance. Think about how far Mars seems when we talk about sending astronauts there. The journey would take about 7 to 9 months with current rocket technology. People talk about a Mars mission as one of the most ambitious engineering projects humanity has ever attempted. And the Kuiper Belt is 55 times wider than that distance at its closest. The distance from Earth to Jupiter at its closest is about 365 million miles. The Kuiper Belt's width is still more than 5 times that. Here's yet another way to feel this. When New Horizons, the fastest spacecraft ever launched from Earth at the time, left Earth in January of 2006 headed for Pluto, it was traveling at about 36,000 miles per hour relative to Earth. Even at that tremendous speed, after getting a gravity assist from Jupiter that boosted its velocity further, it still took New Horizons 9.5 years to reach Pluto. Pluto orbits at roughly 39 AU, which puts it inside the Kuiper Belt, not at its outer edge. Pluto is roughly in the inner to middle region of the classical belt. The outer edge of the classical belt at 50 AU is still 11 AU farther out than Pluto. To cover that additional 11 AU, New Horizons, even at its tremendous velocity, would need several more years. The spacecraft is currently heading outward through the Kuiper Belt, and it will not leave the classical belt region for a long time yet. Even after its Pluto flyby in 2015, it continued on to visit the Kuiper Belt object Arrokoth in January of 2019, and it is still flying through the belt today. That is how wide this region is. A spacecraft traveling at tens of thousands of miles per hour takes years and years to cross it. Now think back to that classroom diagram. In that diagram, the Kuiper Belt is shown as a strip maybe an inch or two wide on the poster. Neptune might be 8 or 10 inches from the Sun. The Kuiper Belt looks like a minor addition. Maybe 5 or 10% of the visual width of the whole solar system. But in reality, the Kuiper Belt's classical extent is about 2/3 the distance from the Sun to Neptune. If the Sun to Neptune distance was shown as 12 inches on a diagram, the Kuiper Belt should stretch an additional 8 inches beyond that. The total solar system out to the edge of the classical belt should be about 20 inches on the diagram, with the Kuiper Belt making up nearly half of it. On almost every diagram you've ever seen, the Kuiper Belt has been compressed down to almost nothing. It's been squeezed and shrunken to fit the poster, to fit the textbook page, to fit the television screen, and in the process, its true scale has been hidden from you. The reason for this compression is understandable. Diagrams need to fit on a page or a screen. If you drew the solar system to scale, showing both the sizes of the planets and the distances between them accurately, the diagram would be completely impractical. The planets would be tiny dots separated by enormous amounts of empty space. The inner planets would be clustered so close to the sun that you couldn't distinguish them. The outer planets would be scattered across the room, and the Kuiper Belt would extend down the hallway. No textbook can print that. No classroom wall can hold it. So the diagrams get compressed. Distances get shrunk. The gaps between planets get reduced so that everything fits neatly on one page. This works fine for teaching kids the order of the planets, but it creates a deeply inaccurate mental picture of the solar system's actual structure. It makes you think the planets are relatively close together and that the Kuiper Belt is a small feature at the edge. The truth is exactly the opposite. The solar system is mostly empty space, and the Kuiper Belt is one of the largest structures within it. Here's a thought experiment that might help. Imagine you're standing on the sun, which obviously you can't do, but imagine it. You look out toward the planets. Earth is 1 AU away. It's a tiny blue dot, barely visible. Jupiter is about 5 AU away, a small bright point. Neptune is 30 AU away, incredibly faint, almost invisible in the darkness. Now you look past Neptune. The Kuiper Belt begins. It stretches from 30 AU to 50 AU. You scan this enormous region of space and you realize something shocking. The width of the zone you're scanning, from Neptune's orbit to the outer edge of the classical belt, is larger than the distance from you to Uranus. It's larger than the distance from you to Saturn. It's 2/3 of the entire distance from you to Neptune. And this region is filled with objects, small icy bodies scattered across this immense volume. But they're so spread out, so far apart from each other, that from your vantage point on the sun, you'd see nothing. Absolutely nothing. The Kuiper Belt would be invisible to you despite containing hundreds of thousands of objects. That's how vast and how empty it is simultaneously. Let me give you one more sense of scale before we move on. If you were to shrink the solar system so that the sun was the size of a basketball, sitting in the center of a room, the Earth would be a tiny grain of sand about 86 feet away. Jupiter would be a marble about 450 feet away, nearly the length of a football field and a half. Neptune would be a small bead about half a mile away. And the classical Kuiper Belt would extend from that half-mile mark all the way out to about 9/10 of a mile from the basketball. The Kuiper Belt in this model would span a distance of roughly 1/3 of a mile. You'd have to walk for several minutes to cross it, and along the way, the objects within it would be so tiny and so widely spaced that you'd never find one without precise coordinates. You'd just be walking through empty space, surrounded by nothing visible, for block after block. This is what the classroom diagram hides from you. This is the lie of the flat poster. The Kuiper Belt is not a small detail at the edge of the solar system. It is a region of space that rivals the entire planetary system in scale. It's wider than the distance from the Sun to Uranus. It's wider than the distance from the Sun to Saturn. It's wider than every gap between every pair of planets in the inner solar system combined. If you added up the distance from Mercury to Venus, Venus to Earth, Earth to Mars, Mars to Jupiter, and Jupiter to Saturn, you'd still come up short of the Kuiper Belt's classical width. That's not a footnote. That's not an afterthought. That's a major component of our solar system that has been systematically minimized in the public imagination because of how we draw pictures. And there's another dimension to this distortion that most people never consider. When you see the solar system diagram, it's flat. It's a two-dimensional image, showing the planets in a line or in concentric circles. This makes the Kuiper Belt look like a ring, a flat band encircling the Sun in the same plane as the planets. But the Kuiper Belt is not perfectly flat. Many of its objects have orbits that are tilted relative to the plane of the planets, sometimes significantly. The belt has a vertical thickness to it. It puffs up above and below the ecliptic plane, giving it a three-dimensional structure more like a thick donut than a thin disk. We'll explore this three-dimensional shape in much more detail later, but for now, the important thing to understand is that the flat diagram doesn't just compress the Kuiper Belt horizontally. It also flattens it vertically. The real Kuiper Belt occupies a volume of space, not just a surface, and that volume is absolutely colossal. The total volume of space enclosed within the Kuiper Belt's classical boundaries, from 30 to 50 AU, accounting for its vertical extent, is measured in the hundreds of trillions of cubic astronomical units. That's a number so large it has no intuitive meaning. But here's a comparison that might help. The volume of space inside Neptune's orbit, the space that contains the Sun and all the planets, is roughly 113,000 cubic AU if you model it as a sphere. The volume of the classical Kuiper Belt shell, extending from 30 to 50 AU, is several times larger than that. The Kuiper Belt occupies more volume than the entire planetary solar system. More volume, not slightly more, significantly more. The region of space containing all the planets you've ever heard of, every world that humanity has studied and sent spacecraft to, that entire zone is smaller in volume than the Kuiper Belt that surrounds it. And most people have never been told this because the diagrams don't show it. The posters don't convey it. The textbook illustrations make it look like the Kuiper Belt is a modest feature at the outskirts. In reality, it's the outskirts that are bigger than the town. This is the fundamental shift in perspective that we need to make before we can talk about what's actually out there in the Kuiper Belt. We need to stop thinking of it as a small ring past Neptune and start thinking of it as what it truly is. An immense, sprawling region of the solar system that makes the planetary zone look compact and cramped by comparison. The planets are clustered relatively close to the Sun, huddled in the inner 30 AU of a much larger structure. The Kuiper Belt extends the solar system far beyond that, nearly doubling the effective radius of the Sun's domain in terms of significant populations of orbiting objects. Everything you're about to learn about the objects in the belt, about its structure, about how it was shaped, about what it tells us, all of it becomes far more meaningful once you understand this basic truth about scale. The Kuiper Belt is not small. It is enormous. It's one of the largest structures in our solar system. And the only reason most people don't know this is because of a well-meaning but deeply misleading diagram that hangs on classroom walls around the world. So let's leave that diagram behind. Let's stop imagining the Kuiper Belt as a thin ring at the edge of a poster. Instead, picture it as it really is. A vast, dark, cold expanse of space, stretching across billions of miles, so wide that even our fastest spacecraft needs years to cross it. So enormous that it contains more volume than all the space occupied by the planets combined. That is the Kuiper Belt. And we've only just begun to understand it. Now that you understand how vast the Kuiper Belt is in terms of sheer distance and volume, you might be picturing something dramatic out there. Maybe you're imagining a dense field of icy boulders drifting through the darkness, packed together like rocks in a riverbed. Maybe you're thinking of something like the asteroid belt in movies, where spaceships have to dodge and weave between tumbling chunks of debris that fill the screen from edge to edge. If that's what you're imagining, you need to let that image go completely. Because the reality of the Kuiper Belt is almost the opposite of that picture. The Kuiper Belt is overwhelmingly, staggeringly, almost incomprehensibly empty. Let me explain what I mean. Astronomers estimate that the Kuiper Belt contains somewhere around 100,000 objects, larger than 100 kilometers across. 100 kilometers is about 62 miles. That's roughly the distance from one end of a major city to the other. So we're talking about objects the size of small countries or large metropolitan areas. 100,000 of them scattered throughout the belt. On top of that, there are likely millions of objects in the range of 1 to 100 kilometers, and possibly trillions of smaller bodies, icy fragments just a few meters or even centimeters across, remnants from the formation of the solar system 4.5 billion years ago. Those numbers sound impressive. 100,000 large objects, millions of medium ones, trillions of tiny ones. It sounds like the Kuiper Belt should be crowded. It sounds like there should be objects everywhere you look. But remember what we established about the volume of this region. The Kuiper Belt stretches from 30 to 50 astronomical units from the Sun. It has a vertical thickness of several astronomical units above and below the plane of the planets. The total volume of space it occupies is measured in hundreds of trillions of cubic astronomical units, and one astronomical unit is 93 million miles. A cubic astronomical unit is a cube 93 million miles on each side. The volume we're talking about is so vast that even trillions of objects scattered throughout it would be separated by enormous distances. Let's put some numbers to this to make it real. If you take the estimated number of significant Kuiper Belt objects, the ones larger than a few kilometers across, and spread them evenly through the volume of the classical belt, the average distance between neighboring objects works out to roughly tens of millions of miles. Not thousands of miles, not hundreds of thousands of miles, tens of millions of miles. The nearest Kuiper Belt object to any given other Kuiper Belt object is, on average, farther away than the distance from Earth to Mars at its closest approach. Think about what that means for a spacecraft flying through the belt. When New Horizons passed through the Kuiper Belt, it didn't need to dodge anything. There was nothing to dodge. The spacecraft flew through billions of miles of essentially empty space, encountering nothing unless it was specifically aimed at a target. Finding Arakoth, the small Kuiper Belt object that New Horizons visited in 2019, required years of searching with the Hubble Space Telescope just to identify a suitable target that happened to lie close enough to New Horizons' trajectory. Even then, the spacecraft had to make precise course corrections to hit its target. If New Horizons had simply flown straight ahead without aiming at anything in particular, it could have crossed the entire classical Kuiper Belt without ever coming close to a single object large enough to see. This is fundamentally different from what most people picture when they hear the word belt. The asteroid belt between Mars and Jupiter has the same problem with public perception. Movies show the asteroid belt as a dense field of tumbling rocks that you have to navigate carefully. In reality, the asteroid belt is also mostly empty space. Spacecraft have flown through it numerous times without incident and without needing to avoid anything. The average distance between asteroids in the main belt is about 600,000 miles. You'd have to be spectacularly unlucky to hit one by accident, but the Kuiper Belt makes even the asteroid belt look crowded by comparison. The Kuiper Belt is much wider than the asteroid belt, much thicker in vertical extent, and while it contains more total mass, that mass is spread across a vastly larger volume. The density of objects in the Kuiper Belt is far lower than in the asteroid belt. If the asteroid belt is a mostly empty room with a few marbles scattered on the floor, the Kuiper Belt is a warehouse the size of a small city with those same marbles spread throughout it. You could walk through that warehouse for years and never step on one. Here's an analogy that might help. Imagine the entire classical Kuiper Belt, from 30 to 50 AU, shrunk down so that it fits inside a sphere the size of Earth. Now take all the known and estimated Kuiper Belt objects and shrink them proportionally. In this model, the larger objects, the ones 100 kilometers across, would be smaller than grains of sand, and they would be scattered throughout the volume of the Earth, with average separations of dozens of miles between them. You could pick a random point inside this Earth-sized model, and the nearest Kuiper Belt object would likely be farther away than you could see. You could wander through this model for your entire life and never encounter a single one, unless you had a map and deliberately searched. That is how empty the Kuiper Belt is. It's a region of space that is overwhelmingly nothing. Void, vacuum, darkness, with occasional tiny frozen objects separated by distances that dwarf anything in our everyday experience. So when I say the Kuiper Belt is enormous, I need you to hold two ideas in your head at once. It's enormous in extent, stretching across billions of miles, and it's enormous in emptiness. The two go together. The belt is big because it contains a lot of space, but most of that space contains absolutely nothing. The objects within it are islands in an ocean so wide that the islands might as well not exist from most vantage points. And yet, those islands are fascinating. Because despite the emptiness, the objects that do exist in the Kuiper Belt are some of the most scientifically valuable bodies in the entire solar system. They are frozen time capsules, remnants from the earliest days of the solar system's formation, preserved in the deep freeze of the outer solar system for 4.5 billion years. While the inner solar system has been geologically active, with volcanism, plate tectonics, atmospheric erosion, and countless impacts reshaping the surfaces of planets and moons, the outer solar system has been relatively quiet. Objects in the Kuiper Belt have been sitting in the cold darkness essentially untouched since they formed. They are among the most pristine materials we can study. Looking at a Kuiper Belt object is like looking at a fossil from the birth of the solar system. But before we talk about what these objects look like up close, it's worth pausing to appreciate just how difficult it is to find them in the first place. Because the emptiness and remoteness of the Kuiper Belt don't just make it sparse, they make it nearly invisible to us here on Earth. Detecting Kuiper Belt objects is one of the most painstaking challenges in observational astronomy. Think about what we're dealing with. These objects are billions of miles from the Sun. They receive almost no sunlight. At 40 AU, the intensity of sunlight is 1,600 times weaker than it is on Earth. Whatever dim light does reach a Kuiper Belt object, only a tiny fraction bounces back toward us. These are not bright, reflective bodies, and many of them are covered in dark, reddish organic compounds that absorb most of the light that hits them. The result is that even a large Kuiper Belt object, something hundreds of miles across, appears from Earth as an incredibly faint point of light. Far too dim to see with the naked eye, too dim even for most amateur telescopes. Only the largest professional telescopes in the world, equipped with highly sensitive cameras and operated under ideal conditions, can detect them at all. And detecting them is only the first problem. The second problem is telling them apart from everything else in the sky. When you point a powerful telescope at a patch of sky in the direction of the Kuiper Belt, you see thousands upon thousands of background stars and distant galaxies. Each one is a point of light. A Kuiper Belt object is also a point of light, but one that's vastly fainter than most of the stars in the same field of view. The only way to identify it is by its motion. Stars are so far away that they appear fixed in place over human timescales. A Kuiper Belt object, by contrast, is close enough that it moves very slightly against the stellar background over the course of hours or days as it orbits the Sun. But this motion is incredibly slow. At 40 AU, an object creeping along its orbit might shift by only a tiny fraction of a degree per day. To spot it, astronomers have to take multiple images of the same patch of sky, separated by hours or nights, and then compare them pixel by pixel, looking for anything that has shifted position even slightly. This is how the first Kuiper Belt object beyond Pluto was discovered. In 1992, astronomers David Jewett and Jane Liu had been searching for years, painstakingly photographing patches of sky near the ecliptic plane and comparing images taken on different nights, looking for faint points of light that moved. Night after night, year after year, they found nothing. The search required enormous patience and dedication because the odds of pointing your telescope at exactly the right spot to catch one of these faint, sparse, slow-moving objects were incredibly low. When they finally detected 1992 QB1, it was a tiny smudge that had shifted just slightly between exposures. It didn't look like much, but it was the first confirmed member of a vast population that would reshape our understanding of the solar system. Even today, with far more powerful telescopes and sophisticated digital cameras and automated detection software that can scan millions of pixels looking for moving objects, discovering new Kuiper Belt objects remains difficult. We've catalogued a few thousand so far, but astronomers estimate that represents only a small fraction of the total population, perhaps a few percent of the objects larger than 100 kilometers across. The vast majority remain undiscovered, too faint or too far away or in parts of the sky we haven't surveyed deeply enough. Every year, new objects are added to the catalogue, but the belt is so enormous and its contents so faint that a complete census may never be possible with current technology. So what are these objects made of? Primarily ice, but not just water ice. Kuiper Belt objects contain a complex mixture of frozen, volatile compounds. Water ice is the most common, forming the structural backbone of most objects. But layered on top of and mixed within that water ice are frozen methane, frozen nitrogen, frozen carbon monoxide, frozen carbon dioxide, frozen ammonia, and various organic compounds, complex carbon-based molecules that formed in the cold outer reaches of the primordial solar nebula. The exact composition varies from object to object, depending on where it formed, how it was heated or processed over time, and what collisions it experienced. But in general, Kuiper Belt objects are dirty snowballs. They're mixtures of ice, rock, and organic material, frozen solid at temperatures around minus 220 degrees Celsius, or about minus 360 degrees Fahrenheit. At these temperatures, even substances that are gases on Earth, like methane and nitrogen, freeze as hard as rock. The most famous Kuiper Belt object by far is Pluto. For 76 years, from its discovery in 1930 to its reclassification in 2006, Pluto was considered the 9th planet of our solar system. When the International Astronomical Union reclassified it as a dwarf planet, it was controversial. Many people felt attached to Pluto as a planet, but the reclassification happened because astronomers had discovered other objects in the Kuiper Belt that were comparable in size to Pluto, and it became clear that Pluto was not a unique object orbiting alone at the edge of the solar system. It was the largest known member of a vast population of similar icy bodies. Pluto orbits the Sun at an average distance of about 39.5 AU. Its orbit is noticeably elliptical, ranging from about 29.7 AU at its closest to the Sun to about 49.3 AU at its farthest. This means Pluto actually dips inside Neptune's orbit for part of its 248 Earth-year orbital period. Pluto was closer to the Sun than Neptune from 1979 to 1999, for instance. Despite this orbital overlap, Pluto and Neptune never come close to colliding because Pluto's orbit is tilted about 17 degrees relative to the plane of the planets, and Pluto is locked in a precise orbital resonance with Neptune that keeps them separated. We'll talk more about that resonance later. But for now, the important thing is that Pluto is firmly a Kuiper Belt object. It lives in the belt. It's part of the belt's population, and it's the one we know best. In July of 2015, NASA's New Horizons spacecraft flew past Pluto after its 9.5-year journey from Earth. What it found stunned the scientific community. Pluto was not the dead, featureless ice ball that many had expected. It was a complex, geologically active world with a stunning variety of terrain. The most iconic feature was a vast heart-shaped region called Tombor Regio. Its left lobe, a huge basin called Sputnik Planitia, is a plain of frozen nitrogen ice covering an area larger than Texas. This plain appeared remarkably smooth, almost completely free of impact craters, which told scientists something extraordinary. The surface had to be young. On a world 4.5 billion years old, a crater-free surface means something is erasing the craters. Something is resurfacing the terrain. Sputnik Planitia showed evidence of convection, a process where the frozen nitrogen ice slowly churns, warm ice rising from below and cool ice sinking from above, gradually recycling the surface and erasing craters over time. This was active geology on a world billions of miles from the Sun, in temperatures cold enough to freeze nitrogen solid. New Horizons also revealed towering mountains on Pluto. Mountains made of water ice, rising as high as 11,000 feet, comparable to the Rocky Mountains on Earth. At the temperatures on Pluto's surface, water ice behaves like rock. It's hard enough to form mountain ranges that persist for geological ages. Meanwhile, the nitrogen and methane ices that cover much of the surface are softer and flow more easily, creating glaciers and plains. Pluto also has a thin atmosphere, primarily nitrogen with traces of methane and carbon monoxide. This atmosphere expands when Pluto is closer to the Sun and contracts as it moves farther away. New Horizons captured images of haze layers in Pluto's atmosphere, illuminated by the Sun as the spacecraft looked back after its flyby. These haze layers extend hundreds of miles above the surface and are created by ultraviolet sunlight, breaking apart methane molecules in the upper atmosphere, which then recombine into more complex hydrocarbons that settle down as a reddish organic haze. This haze gives Pluto its distinctive reddish-brown color in many areas. Pluto has 5 known moons. The largest, Charon, is so big relative to Pluto that the two are sometimes called a binary system. Charon has a diameter of about 753 miles, roughly half of Pluto's diameter of about 1,473 miles. The two orbit each other around a point in space between them, a common center of mass that lies outside Pluto's surface. Charon's surface showed its own surprises, including a massive canyon system stretching across much of the moon, and a reddish polar cap that scientists believe is created by methane gas escaping from Pluto's atmosphere, drifting to Charon, freezing on the cold poles, and then being chemically processed by ultraviolet radiation into reddish organic compounds called tholins. Pluto was just the beginning. But it's not the only dwarf planet in the Kuiper Belt. Eris, discovered in 2005 by astronomer Mike Brown and his team, was the discovery that ultimately triggered Pluto's reclassification. Eris orbits much farther out than Pluto, at an average distance of about 68 AU from the Sun, though its highly elliptical orbit brings it as close as 38 AU, and takes it as far as 97 AU. Eris is slightly smaller than Pluto in diameter, about 1,445 miles across, but it's actually more massive. Eris contains about 27% more mass than Pluto, packed into a slightly smaller volume, making it denser. This higher density suggests Eris contains a greater proportion of rock relative to ice compared to Pluto. Eris has one known moon, Dysnomia, which orbits it once every roughly 16 days. Eris's surface is covered in frozen nitrogen and methane, but because it spends most of its orbit so far from the Sun, its atmosphere, if it has one, is almost certainly completely frozen onto the surface. When Eris is at its most distant, temperatures drop so low that even nitrogen, already a frozen solid on Pluto's surface, becomes even harder and more rigid. Eris is a world locked in the deepest freeze imaginable, a frozen relic that rarely, if ever, experiences any form of surface activity. Makemake, discovered in 2005, orbits at about 45.8 AU from the Sun. It has a diameter of roughly 890 miles, making it about 2/3 the size of Pluto. Makemake's surface is covered in frozen methane, ethane, and possibly nitrogen. It appears to have a reddish color in some areas, likely from the same kind of organic tholin compounds found on Pluto. Makemake was one of the objects whose discovery helped establish that Pluto was not unique, but part of a population. It has one known small moon, provisionally designated MK2, discovered in 2016 using the Hubble Space Telescope. Haumea is perhaps the strangest of the Kuiper Belt's dwarf planets. It orbits at about 43.1 AU and has a shape that is dramatically elongated. Haumea is not a sphere. It's shaped more like an egg or an elongated ellipsoid, stretching about 1,440 miles along its longest axis, but only about 700 miles along its shortest. This unusual shape is caused by its extremely rapid rotation. Haumea spins once every 3.9 hours, making it one of the fastest rotating large objects in the solar system. This rapid rotation flings material outward, stretching the body along its equator. Haumea also has 2 small moons, named Hiyaka and Namaka, and it has a ring. Haumea is one of only a handful of objects in the solar system known to possess a ring system, and it's the only dwarf planet known to have one. The ring was discovered in 2017 during a stellar occultation, when Haumea passed in front of a distant star and astronomers carefully measured how the star's light dimmed. Beyond these dwarf planets, the Kuiper Belt is populated by a vast array of smaller objects. These range from bodies a few hundred kilometers across down to tiny fragments just a few meters wide. Most of these objects are too small and too faint to detect with current telescopes. We know they must exist based on models of how the solar system formed and based on observations of the larger objects that we can see. The total mass of the Kuiper Belt is estimated at roughly 1/10 the mass of Earth. That might not sound like much, but remember, this mass is spread across a volume of space larger than the entire planetary solar system. The belt's low total mass is part of why it's so empty. There simply isn't that much material out there to fill the enormous space it occupies. The composition of these smaller objects tells us about the conditions in the outer solar nebula when the solar system was forming. 4.5 billion years ago, the Sun was surrounded by a vast rotating disk of gas and dust. Close to the Sun, where temperatures were high, only rocky materials and metals could survive as solids. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky. Farther out, where temperatures drop below certain thresholds called frost lines, various ices could survive. Beyond the water frost line, water could exist as solid ice. Beyond the methane frost line, methane could freeze. Beyond the nitrogen frost line, nitrogen could freeze. The Kuiper Belt lies far beyond all of these frost lines. It's a region where essentially every volatile compound that existed in the solar nebula could freeze into solid form. This is why Kuiper Belt objects are so rich in ices. They formed in a region where everything that could freeze did freeze. Water, methane, nitrogen, ammonia, carbon monoxide, carbon dioxide, all of it froze out of the nebula gas and accumulated onto tiny grains that gradually stuck together through gentle collisions, building up larger and larger bodies over millions of years. This process, called accretion, is how all the planets and small bodies in the solar system formed. But in the Kuiper Belt, the process was slower and less efficient than closer to the Sun. The material was more spread out, collisions were less frequent, and gravitational attraction was weaker because the individual pieces were small and far apart. As a result, the Kuiper Belt never formed a large planet. Instead, it produced a vast population of small to medium-sized icy bodies, the largest of which are the dwarf planets, but most of which are much smaller. The New Horizons mission gave us our most intimate look at one of these smaller objects when it flew past Arakoth, formerly known as Ultima Thule, on January 1st, 2019. Arakoth is a small Kuiper Belt object about 22 miles long, orbiting at about 44.6 AU from the Sun. Its shape was immediately striking. Arakoth is a contact binary, two roughly spherical lobes joined together like a snowman. The larger lobe is about 13.7 miles across, and the smaller lobe is about 8.7 miles across. They're connected by a narrow neck where the two bodies gently merged. This shape told scientists something remarkable about how objects formed in the outer solar system. The gentle merging of Arakoth's two lobes suggests that the collision that joined them was very slow, probably just a few miles per hour. This is consistent with the formation process where small objects in the solar nebula slowly spiral toward each other, drawn together by their mutual gravity and by interactions with the surrounding gas, and merge gently rather than smashing together violently. Arakoth's surface showed no signs of violent impact. No fractures, no debris fields, just a gentle joining of two objects that drifted together in the ancient cold of the outer solar system. Arakoth's surface is uniformly reddish, colored by organic tholins, the same kind of radiation-processed organic compounds found on Pluto and many other Kuiper Belt objects. Its surface is old, covered in small craters accumulated over billions of years, but with no signs of geological activity. Unlike Pluto, which showed surprising complexity, Arakoth is a simple, ancient body that has remained essentially unchanged since it formed. It's a pristine relic of the solar system's birth, a 4.5 billion year old time capsule preserved in the deep freeze of the Kuiper Belt. The contrast between Pluto and Arakoth illustrates something important about the Kuiper Belt's population. The belt contains an enormous range of objects, from worlds large enough to have complex geology, atmospheres, and moons, down to tiny frozen fragments that have barely changed since the solar system was born. The dwarf planets are the headliners, the objects that grab attention and make headlines. But the smaller bodies are arguably more scientifically important because they preserve the original conditions of the solar nebula in a way that larger, geologically active bodies do not. Together, these objects, the dwarf planets, the medium-sized bodies, and the trillions of tiny icy fragments, form a population that is spread incredibly thin across an incredibly vast region of space. Each one is a frozen world unto itself, carrying information about the earliest days of the solar system locked into its composition, its shape, and its orbit. And each one is separated from its nearest neighbor by distances measured in millions of miles. If you could somehow visit every known Kuiper Belt object, one after another, you would spend the overwhelming majority of your time traveling through absolute nothingness. Empty, dark, silent vacuum, stretching on and on and on, with temperatures barely above absolute zero. In a region where sunlight is so faint that noon would look like deep twilight on Earth. This is the paradox of the Kuiper Belt. It is full and empty at the same time. Full of scientifically precious objects, empty of nearly everything else. A vast frozen archive scattered across billions of miles of space, so sparsely that finding any individual object within it is like finding a specific snowflake in a blizzard that covers an entire continent. The Kuiper Belt is not a wall. It's not a dense field. It's not a barrier that spacecraft need to navigate through. It is an immense, sparse scattering of frozen remnants, each one carrying secrets from the dawn of the solar system. Separated by gulfs of empty space so wide that the objects might as well exist in separate universes. And understanding this dual nature, the enormity of the region combined with the sparseness of its contents, is essential to understanding what the Kuiper Belt truly is. It is not a crowded suburb of the solar system. It is a vast, lonely wilderness where tiny frozen worlds drift in silence, separated from each other by millions of miles of nothing, orbiting a distant sun that appears as little more than a bright star in an otherwise black sky. That is the Kuiper Belt, and we are only beginning to explore it. So the Kuiper Belt is enormous, and it's overwhelmingly empty. But knowing those two things still doesn't prepare you for what comes next, because the Kuiper Belt is not a simple, uniform ring of debris either. It is a complex, sculpted, three-dimensional structure with distinct populations, gaps, concentrations, and orbital families, all carved into existence by the gravitational influence of one planet, Neptune. When most people picture the Kuiper Belt, if they picture it at all, they imagine something like a flat disk of material encircling the sun, sitting neatly in the same plane as the planets. A ring of icy debris, more or less evenly distributed, stretching from Neptune's orbit outward. Simple, clean, uniform. But the actual Kuiper Belt looks nothing like that. It's messy. It's structured. It has zones where objects cluster and zones that are nearly empty. Some objects orbit in neat circles close to the plane of the planets. Others follow wildly elongated, tilted paths that carry them far above and below the planetary plane and far inward and outward from the sun. The belt has a vertical thickness to it, puffing up above and below the ecliptic, giving it a three-dimensional shape that's more like a thick, lumpy donut than a thin, flat ring. And virtually all of this structure, every gap, every concentration, every orbital tilt, can be traced back to the gravitational fingerprints of Neptune. To understand how Neptune shaped the Kuiper Belt, we need to first understand the different populations of objects that live within it. Astronomers have identified several distinct groups based on their orbital properties, and each group tells a different story about how it got to where it is. The first and most straightforward group is the classical Kuiper Belt objects, sometimes called cubewanos. The name cubeano comes from the first object discovered in this group, 1992 QB1, which was also the first Kuiper Belt object ever found after Pluto. Astronomers pronounced the designation QB10, which eventually became Cubeano, and the name stuck as a label for the entire class. Classical Kuiper Belt objects orbit the Sun at distances roughly between about 42 and 48 AU. Their orbits are relatively circular, meaning they don't swing dramatically closer to or farther from the Sun as they go around. And many of them have orbits that are relatively close to the ecliptic plane, the flat plane in which the planets orbit. These are considered the most undisturbed members of the Kuiper Belt. They occupy orbits that are thought to be close to where they originally formed, 4.5 billion years ago. They haven't been significantly pushed or pulled by Neptune's gravity. They're just sitting out there in relatively stable, well-behaved orbits, slowly circling the Sun in the deep cold. The classical belt is sometimes thought of as the quiet zone of the Kuiper Belt, the region where objects have been left more or less alone since the solar system's early days. But even within the classical belt, there's structure. Astronomers have noticed that the classical belt actually has two subpopulations. There's a cold classical population and a hot classical population. These names have nothing to do with temperature. Out in the Kuiper Belt, everything is frozen solid regardless of which population it belongs to. The terms cold and hot refer to the orbits. In orbital mechanics, a cold population has objects on nearly circular, low inclination orbits, meaning they stay close to the ecliptic plane and don't deviate much from a perfect circle. A hot population has objects on more elliptical, more inclined orbits. They wander farther from the ecliptic plane and have more elongated paths around the Sun. The cold classical objects are the most pristine, most undisturbed population in the Kuiper Belt. They have very low orbital inclinations, typically less than about 5 degrees from the ecliptic plane. Their orbits are nearly circular. They tend to be redder in color than other Kuiper Belt objects, suggesting their surfaces have been heavily processed by cosmic radiation over billions of years without being disrupted or resurfaced. Many of them are binaries, two objects orbiting each other as they jointly orbit the Sun. The high rate of binaries in the cold classical population suggests these objects formed gently. In low-velocity environments where pairs of objects could gravitationally capture each other without being torn apart. The hot classical objects, by contrast, have higher orbital inclinations, sometimes exceeding 20 or 30 degrees from the ecliptic plane. Their orbits are more elliptical. They tend to be less red and more diverse in color. These objects were probably scattered or stirred up at some point in the solar system's history, excited out of their original calm orbits by gravitational interactions. The question is, what stirred them? And the answer, as with nearly everything about the Kuiper Belt structure, is Neptune. The second major population in the Kuiper Belt is the resonant objects. These are objects whose orbits are locked in precise mathematical relationships with Neptune's orbit. The most famous resonant group is the Plutinos, named after Pluto because Pluto is the largest and most well-known member. Plutinos are locked in what's called a 3-to-2 mean motion resonance with Neptune. This means that for every 3 orbits Neptune completes around the Sun, a Plutino completes exactly 2. Pluto, for instance, takes about 248 Earth years to orbit the Sun. Neptune takes about 165 years. The ratio of their orbital periods is very close to 3-to-2. This resonance is not a coincidence, it's a gravitational lock. Neptune's gravity has captured these objects into this precise orbital relationship, and the resonance protects them. Here's why that matters. Pluto's orbit actually crosses Neptune's orbit. At its closest approach to the Sun, Pluto is about 29.7 AU away, which is closer than Neptune's average distance of about 30 AU. You might think this would eventually lead to a collision, or at least a close encounter between Pluto and Neptune. But the 3-2 resonance prevents this. Because of the precise timing of their orbits, whenever Pluto is at its closest to the Sun and crossing Neptune's orbital path, Neptune is always on the opposite side of its orbit, far away. The two never come anywhere near each other. The resonance acts like a cosmic traffic signal, ensuring that Pluto and Neptune are always in different lanes when their paths cross. This gravitational protection has kept Pluto safe for billions of years, despite its orbit nominally intersecting Neptune's. The Plutinos are not the only resonant group. There are objects in 2-to-1 resonance with Neptune, meaning they complete one orbit for every 2 of Neptune's. These orbit at about 47.8 AU. There are objects in 5-to-3 resonance, 7-to-4 resonance, 5-to-2 resonance, and many other ratios. Each resonance corresponds to a specific distance from the Sun, and at each of these distances, there's a cluster of objects locked into that particular orbital rhythm. If you could map the Kuiper Belt and plot where objects are concentrated, you'd see these resonant populations standing out like peaks in a graph. Clusters of objects at specific distances, corresponding to specific resonances with Neptune. The existence of these resonant populations is one of the most striking features of the Kuiper Belt structure. They tell us that Neptune's gravitational influence extends far beyond the planet itself, reaching out across billions of miles to organize the orbits of objects that are vastly far away. Neptune is about 30 AU from the Sun. The Plutinos orbit at about 39 AU. The 2-to-1 resonant objects orbit at about 48 AU. Neptune is sculpting the orbital structure of objects that are 9, 18, or even more AU away from it. This is the invisible hand of gravity operating across distances that are almost impossible to imagine on a human scale. The third major population is the scattered disk objects. These are bodies that have been flung onto extreme orbits by close gravitational encounters with Neptune. Unlike the classical belt objects, which sit in relatively calm, well-behaved orbits, scattered disk objects have orbits that are highly elliptical and often highly inclined. Their closest approach to the Sun might be around 30 to 35 AU, similar to Neptune's orbit, but their farthest point can extend to 100, 200, or even several hundred AU from the Sun. These objects spend most of their time far from the Sun in the cold outer reaches, plunging briefly inward through the Kuiper Belt region, before swinging back out into the distant darkness. Eris, the dwarf planet we discussed earlier, is often classified as a scattered disk object because of its extreme orbit. Its closest approach to the Sun is about 38 AU, but its farthest point is about 97 AU. It swings inward through the Kuiper Belt region, then retreats to nearly 100 AU, far beyond the classical belt's outer edge. Eris spends most of its 559 Earth-year orbit in the distant outer regions, only briefly passing through the classical belt zone during each orbit. The scattered disk is important because it shows the violence of Neptune's influence. These objects didn't end up on their extreme orbits by accident. They were thrown there by Neptune. At some point in the past, each scattered disk object had an encounter with Neptune that was close enough or repeated enough to dramatically alter its orbit. Neptune's gravity grabbed them and flung them outward, onto paths that carry them far from the relatively ordered zone of the classical belt. Now, here's where the story gets really interesting, because the question isn't just how Neptune influences the Kuiper Belt today. The question is how Neptune got to where it is in the first place, and the answer to that question transforms our entire understanding of the Kuiper Belt structure. For decades after the Kuiper Belt was first theorized, scientists assumed the solar system had always looked roughly the way it does today. The planets formed where they are, the Kuiper Belt formed beyond Neptune, and everything has been sitting in roughly the same configuration for 4.5 billion years. But in the late 1990s and early 2000s, This picture was shattered by a series of theoretical discoveries that fundamentally changed our understanding of solar system history. The breakthrough came from computer simulations. When scientists tried to model the formation of the Kuiper Belt using the assumption that Neptune had always been at 30 AU, the models didn't work. They couldn't reproduce the structure of the belt that we actually observe. The models predicted the wrong distributions of objects, the wrong orbital characteristics, the wrong total mass. Something was missing from the picture. The key insight came when scientists allowed the planets to move. What if the giant planets didn't form where they are today? What if they formed in a more compact configuration, closer together and closer to the Sun, and then migrated outward to their current positions over time? When scientists ran simulations with planetary migration, everything clicked. The models suddenly produced Kuiper Belt structures that matched observations. The resonant populations, the hot and cold classical populations, the scattered disk, all of it emerged naturally from simulations where Neptune migrated outward. The most influential model of this process is called the Nice model, named after the city of Nice in France where it was developed. The Nice model proposes that the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, originally formed in a much more compact arrangement, all within about 15 to 20 AU of the Sun. Beyond them was a massive disk of icy planetesimals, small bodies left over from planet formation, extending outward for many AU. This disk contained far more mass than the current Kuiper Belt, perhaps 35 to 50 times the mass of Earth. Over time, gravitational interactions between the planets and this disk caused the planets to migrate. Jupiter, being the most massive, moved slightly inward. Saturn, Uranus, and Neptune moved outward. Neptune, starting from perhaps somewhere around 20 AU or even closer, migrated outward toward its current position at 30 AU. As it moved, Neptune's gravity plowed through the disk of icy bodies like a snowplow pushing through snow. Some objects were captured into resonances and pushed outward along with Neptune, surfing on the waves of its gravitational influence. Others were scattered onto wild orbits. Others were ejected from the solar system entirely. The process was slow by human standards, taking tens of millions of years, but violent by solar system standards. The structure of the outer solar system was completely rearranged. This migration explains the resonant populations perfectly. As Neptune moved outward, its resonant zones moved with it. Objects that happened to be at the right distance would get swept up into a resonance and carried along. The 3-2 resonance with Neptune, the one that Pluto is locked in, swept through the disk as Neptune migrated. Pluto and the other Plutinos were captured into this resonance during the migration and have been locked in ever since. They didn't form at 39 AU. They were placed there by Neptune's outward march. The migration also explains the hot and cold classical populations. The cold classical objects, with their calm, circular, low inclination orbits, are thought to have formed in place in the region between about 42 and 47 AU. They were always there, and Neptune's migration didn't disrupt them too severely, because Neptune stopped migrating before reaching their zone. They're the survivors, the objects that were far enough away from Neptune's path to escape major disturbance. Their pristine, undisturbed orbits are evidence that they've been sitting in roughly the same place since the solar system was young. The hot classical objects, by contrast, were probably originally closer to the Sun and were scattered or pushed outward by Neptune's migration. Their higher inclinations and more elliptical orbits are the scars of gravitational stirring. They were disturbed, excited, and displaced by Neptune's passage through the outer disk. They ended up in the classical belt zone, but with more chaotic orbits than the cold population that was already there. The scattered disk is the most direct evidence of Neptune's violence. Scattered disk objects were flung onto their extreme orbits by direct gravitational encounters with Neptune during or after the migration. They represent the objects that came close enough to Neptune to receive a powerful gravitational kick, one strong enough to send them careening onto orbits that take them far from the Sun before bringing them back. Neptune's migration also explains a puzzle about the Kuiper Belt's total mass. The current Kuiper Belt is surprisingly low in mass. Its estimated total mass is only about 1/10 the mass of Earth. But models of planet formation predict that the region beyond Neptune should have contained much more material, enough to build objects much larger than Pluto. Where did all that mass go? Neptune took it. As Neptune migrated outward, its gravity ejected the vast majority of the icy bodies in the outer disk. Most of them were flung onto orbits that took them out of the solar system entirely, lost to interstellar space. Others were thrown inward, where they eventually collided with the giant planets or the Sun, or were ejected by Jupiter. By the time Neptune reached its current position and the migration was complete, more than 99% of the original disk mass had been removed. The Kuiper Belt we see today is the meager remnant, the 1% or less that survived Neptune's gravitational rampage. This means the Kuiper Belt was once far more massive and far more densely populated than it is now. Billions of years ago, the outer solar system was filled with icy bodies, a thick, rich disk of material that extended far beyond where the planets were forming. Neptune's migration through that disk was catastrophic. It scattered, ejected, and destroyed the vast majority of those objects. What remains today, the thin, sparse scattering of icy bodies that we call the Kuiper Belt, is just the ghostly remnant of something much grander. The Kuiper Belt is a ruin, a magnificent, informative ruin that tells us the story of the solar system's violent youth, but a ruin nonetheless. Now, let's talk about the three-dimensional shape of the belt, because this is another aspect that flat diagrams completely fail to convey. The planets orbit the Sun in roughly the same plane, called the ecliptic. This plane is like a flat disk, and on most solar system diagrams, everything appears to sit neatly within it. But the Kuiper Belt is not confined to the ecliptic. Many of its objects, especially those in the hot classical population and the scattered disk, have orbits that are significantly tilted relative to the ecliptic plane. Some objects have orbital inclinations of 10, 20, or even 30 degrees or more. This means their orbits carry them far above and far below the plane of the planets. If you could see the Kuiper Belt from the side, edge on, it wouldn't look like a thin line. It would look like a puffy, extended structure, thick in the middle and tapering toward the edges. The vertical extent of the belt, from its highest points above the ecliptic to its lowest points below, spans several AU. At 50 AU from the Sun, an inclination of 30 degrees corresponds to a vertical displacement of about 25 AU above or below the ecliptic plane. That's 25 times the Earth to Sun distance. Even an inclination of 10 degrees at 50 AU corresponds to a vertical displacement of about 8.7 AU, roughly the distance from the Sun to Saturn. This means the Kuiper Belt is not a flat ring. It's a thick, three-dimensional structure, a torus, roughly speaking, but one that's lumpy and uneven, denser near the ecliptic and thinner farther above and below it. The cold classical population, with its low inclinations, forms a relatively thin component near the ecliptic. The hot classical population and the scattered disk objects puff the belt out into a much thicker structure. Some scattered disk objects have inclinations so high that their orbits are nearly perpendicular to the ecliptic plane, carrying them far from the zone where most Kuiper Belt objects reside. This three-dimensional structure adds enormously to the total volume of space the Kuiper Belt occupies. When we calculated the volume earlier, we were already talking about a region larger than the entire planetary solar system. But that calculation assumed a relatively modest vertical extent. When you account for the high inclination objects that puff the belt up into a thick torus, the total volume of space containing Kuiper Belt objects becomes even more staggering. The belt isn't just wide, it's wide and tall. It extends in every direction, surrounding the inner solar system like a vast, sparse cloud of frozen debris. If you could somehow light up every Kuiper Belt object so that it glowed brightly enough to see, and you could view the solar system from outside, from a vantage point several hundred AU away, what you'd see would surprise you. You wouldn't see a thin, elegant ring like Saturn's rings. You'd see a broad, puffy, loosely defined zone of scattered objects surrounding a tiny, compact cluster of planets near the center. The planets, all of them, would be huddled close to the sun, confined to the inner 30 AU. And surrounding them, extending from 30 to 50 AU and beyond, would be this enormous, diffuse cloud of icy objects, far more spread out in 3 dimensions than any simple diagram would suggest. The cold classical population would appear as a relatively thin band near the ecliptic, but the hot population and scattered objects would blur that band into something much more extended. A hazy, 3-dimensional fog of frozen worlds surrounding the compact planetary core. This image, this picture of a tiny compact planetary system surrounded by an enormous 3-dimensional cloud of icy debris, is the true architecture of our solar system. And it's nothing like the neat, flat, evenly spaced diagram you grew up with. The structure of the Kuiper Belt also preserves information about events that happened during the solar system's formation that we can't learn any other way. The distribution of orbital inclinations tells us about the intensity of the gravitational stirring that occurred during Neptune's migration. The proportion of objects in different resonances tells us about the rate and distance of Neptune's migration. The difference between the cold and hot classical populations tells us about which objects formed in place and which were displaced. The total mass of the belt tells us how much material was ejected during the migration. Even the colors and compositions of Kuiper Belt objects carry information, since objects that formed at different distances from the Sun would have incorporated different mixtures of ices depending on the local temperature. In this sense, the Kuiper Belt is like a crime scene where the evidence has been frozen in place for 4.5 billion years. Every orbit, every inclination, every resonance is a clue, and the detective is Neptune. Neptune's migration through the outer solar system left fingerprints everywhere, and by studying the Kuiper Belt structure, we can reconstruct exactly what happened. The NICE model and its variants have been refined over the past 2 decades, as new observations have provided more data. Different versions of the model propose slightly different migration histories for Neptune. Some suggest a smooth, gradual migration. Others suggest a more violent, sudden jump triggered by a gravitational instability among the giant planets. In some versions of the model, Uranus and Neptune even switch places during the process, with Neptune starting out closer to the Sun than Uranus, and then leapfrogging over it to end up farther out. These details are still being debated, but the broad picture is well established. Neptune migrated outward, and that migration sculpted the Kuiper Belt into the complex structure we observe today. The result is a Kuiper Belt that is not just enormous and empty, but also deeply structured. It carries the scars of the solar system's tumultuous early history in its orbital architecture. Every cluster of objects at a particular resonance, every population with a particular range of inclinations, every gap where objects are conspicuously absent, all of it is a record of what Neptune did as it moved through the outer solar system billions of years ago. The Kuiper Belt is not just a collection of objects. It is a story written in orbits, a narrative of migration, scattering, capture, and survival that plays out across a region of space so vast that light itself needs hours to cross it. Understanding its structure is understanding the history of our solar system. And that history is far more violent, far more dynamic, and far more interesting than anyone imagined before we started looking closely at the frozen worlds beyond Neptune. By now, the Kuiper Belt has revealed itself as something far grander than that thin line on a classroom poster. It is vast, empty, and deeply structured, carved by Neptune over billions of years. But as enormous as all of that is, it's not the end of the story. Because beyond the classical belt, the solar system continues. And what lies beyond makes even the Kuiper Belt look modest. The first thing we need to understand is that the Kuiper Belt doesn't have a sharp outer edge. There's no wall, no boundary, no sudden cutoff where objects stop and empty space begins. Instead, the classical belt gradually thins out around 50 AU, but objects associated with the broader Kuiper Belt population, especially the scattered disk objects we discussed earlier, extend much farther. The scattered disk is sometimes considered a separate structure from the classical Kuiper Belt, and sometimes considered an extension of it. The distinction depends on which astronomer you ask, and which classification scheme they prefer. But physically, the scattered disk is a population of icy bodies on extreme orbits that carry them far beyond the classical belt's outer boundary. Some scattered disk objects have orbits that take them to 100 AU from the Sun. Others reach 200 AU. A few have orbits so elongated that their farthest point from the Sun is 500 AU or more. These objects spend the vast majority of their time in the distant outer reaches of the solar system, far beyond the zone where most Kuiper Belt objects reside. They plunge inward briefly, passing through the classical belt region near their closest approach to the Sun, then swing back out into the darkness for hundreds or thousands of years before returning. The scattered disk effectively extends the Sun's domain of significant orbiting objects far beyond what most people realize. If the classical Kuiper Belt stretches to 50 AU, the scattered disk pushes the boundary of known solar system bodies out to several hundred AU. And even these extreme objects are not the most distant members of the Sun's gravitational family. But between the outer edge of the Kuiper Belt and the inner edge of the Oort cloud, there lies a region that is one of the most mysterious and least understood zones in our entire solar system. From roughly 50 AU out to about 2000 AU, there is an enormous stretch of space where we know almost nothing about what exists. Astronomers sometimes call this the inner Oort cloud or the Hills cloud, after the physicist Jack Hills, who first proposed its existence. This region is too distant for us to detect small objects directly with current telescopes, and it's too close for the Oort cloud models to tell us much about. It's a blind spot, a vast dark gap in our knowledge spanning thousands of astronomical units. Some objects hint at what might lurk in this zone. Sedna, a distant icy body discovered in 2003, has one of the strangest orbits of any known solar system object. Its closest approach to the Sun is about 76 AU, already well beyond the classical Kuiper Belt's outer edge. But its farthest point is roughly 937 AU. Sedna takes approximately 11,400 Earth years to complete a single orbit. It spends almost all of that time in the distant reaches between 100 and 900 AU, a region that no other well-studied population of objects occupies. Sedna is too far from Neptune to have been scattered by Neptune's gravity. Its orbit can't be easily explained by any of the mechanisms that shape the classical belt or the scattered disk. Something else puts Sedna where it is. Several theories have been proposed. One possibility is that a passing star in the early solar system, when the Sun was still in its birth cluster surrounded by other young stars, gravitationally tugged on objects in the outer disk, pulling some of them onto extreme orbits like Sedna's. Another possibility is that an undiscovered planet in the outer solar system is responsible. Sedna's orbit is one of the pieces of evidence that has fueled speculation about Planet 9. Whatever the explanation, Sedna tells us that the region between the Kuiper Belt and the Oort cloud is not empty. There are objects out there, possibly many of them. We just can't see them yet. Far beyond this mysterious intermediate zone, astronomers believe there exists a vast, spherical shell of icy bodies called the Oort cloud. Unlike the Kuiper Belt, which is roughly disc-shaped and concentrated near the ecliptic plane, the Oort cloud is thought to be a sphere. It surrounds the solar system in every direction, above, below, and all around. No Oort cloud object has ever been directly observed. The cloud is too distant and its objects too small and too faint for current telescopes to see. We know it exists, or at least we're very confident it exists, because of comets. Long-period comets, the ones that take thousands or millions of years to complete a single orbit around the Sun, arrive from all directions in the sky, not just from the ecliptic plane. This spherical distribution of comet origins strongly suggests a spherical source region. That source is the Oort cloud. The Oort cloud is estimated to begin at roughly 2000 AU from the Sun and extend outward to perhaps 100,000 AU, possibly even further. 100,000 AU is approximately 1.6 light years. The nearest star to our Sun, Proxima Centauri, is about 4.24 light years away. The outer edge of the Oort cloud may extend roughly 40% of the way to the nearest star. This means the Sun's gravitational influence, tenuous as it is at those distances, reaches an enormous distance into interstellar space. Let's put the Oort cloud scale in context with the Kuiper Belt. The classical Kuiper Belt extends from about 30 to 50 AU. The Oort cloud extends from roughly 2,000 to 100,000 AU. The inner edge of the Oort cloud is about 40 times farther from the Sun than the outer edge of the classical Kuiper Belt. And the Oort cloud's radial extent, from 2,000 to 100,000 AU, is roughly 98,000 AU. That's nearly 5,000 times the width of the classical Kuiper Belt. 5,000 times. If the classical Kuiper Belt were the width of a single page in a book, the Oort cloud would stretch across nearly all the pages of a very thick encyclopedia. The volume difference is even more staggering. The Kuiper Belt, for all its vastness, is a relatively thin structure concentrated around the ecliptic plane, stretching from 30 to 50 AU. The Oort cloud is a sphere extending to 100,000 AU. The volume of a sphere scales with the cube of the radius. The Oort cloud's volume is so many orders of magnitude larger than the Kuiper Belt's volume that the comparison becomes almost absurd. If the Kuiper Belt's volume were a single drop of water, the Oort cloud's volume would be something like a swimming pool, or perhaps a lake. The numbers are so extreme that everyday analogies strain to capture them. And just like the Kuiper Belt, the Oort cloud is overwhelmingly empty. Astronomers estimate the Oort cloud might contain trillions of icy objects, perhaps several trillion, each one a comet nucleus, a dirty snowball of ice and rock, typically a few miles across or smaller. Trillions of objects sounds like a lot, but scattered through a volume of space that extends to 1.6 light years in radius, those trillions of objects are so widely separated that the average distance between any two neighboring Oort cloud objects might be tens of billions of miles. Tens of billions. The Oort cloud makes the Kuiper Belt look crowded. It's a region so sparse that a spacecraft passing through it would have essentially zero chance of encountering anything. You could fly through the Oort cloud for centuries and never come within millions of miles of a single object. The Oort cloud is also thought to be the source of the most spectacular comets we see from Earth. When a passing star or a gravitational disturbance from the galaxy's tidal forces nudges an Oort cloud object just slightly, it can fall inward toward the Sun on an orbit that takes thousands or millions of years to complete. As it approaches the inner solar system, sunlight heats its icy surface, releasing gas and dust that form the glowing coma and tail that we recognize as a comet. Some of the most famous comets in history, visitors like Comet Hale-Bopp in 1997, are thought to have originated in the Oort cloud, making journeys of millions of years to reach the inner solar system and put on a brief show in our skies before retreating back into the distant darkness. So when we talk about the true scale of the Kuiper Belt, we have to acknowledge that the Kuiper Belt is just one layer in a much larger system. It's the innermost major structure beyond Neptune. Beyond it lies the scattered disk, extending to several hundred AU. Beyond the scattered disk lies the mysterious intermediate zone hinted at by objects like Sedna. And beyond that lies the Oort cloud, extending to 100,000 AU or more. Each layer is vastly larger than the one before it. Each layer is vastly emptier, and each layer is vastly more difficult to observe. But even though the Oort cloud dwarfs the Kuiper Belt in size, the Kuiper Belt holds a special place in our understanding of the solar system. The Kuiper Belt is close enough that we can actually observe its objects with powerful telescopes. We can measure their orbits, study their compositions, and even send spacecraft to visit them. The Oort cloud is too distant for any of that. We can't see its objects. We can't measure their orbits directly. We can't send a probe there within any reasonable human time frame. Our knowledge of the Oort cloud is almost entirely theoretical, inferred from the comets it sends our way. The Kuiper Belt, by contrast, is a region we're actively exploring and mapping. It's the frontier of direct exploration in our solar system. And what we've learned there has transformed our understanding of how planetary systems form and evolve. This brings us to one of the most exciting aspects of Kuiper Belt science. Our solar system is not the only one with a debris belt in its outer reaches. Astronomers have detected debris disks around many other stars, rings of dust and ice that glow faintly in infrared light because they absorb starlight and re-emit it as heat. These debris disks are thought to be analogous to our Kuiper Belt. They're the remnants of planet formation around other stars, vast rings of icy and rocky material that were never incorporated into planets. One of the most famous examples is the debris disk around the star Fomalhaut, about 25 light-years from Earth. This disk was imaged directly by the Hubble Space Telescope in 2004. It appears as a bright ring of material orbiting Fomalhaut at a distance of roughly 133 AU from the star. The ring is remarkably narrow and sharply defined, with a clear inner edge and outer edge, suggesting that one or more planets are gravitationally sculpting the disk, keeping its edges sharp. This is directly analogous to how Neptune sculpts the Kuiper Belt. The planet's gravity creates boundaries, sweeping up material that strays too close and maintaining the disk's structure. Another well-known example is the debris disk around Beta Pictoris, about 63 light-years away. This disk extends hundreds of AU from the star and has been studied extensively since the 1980s. It shows warps, gaps, and asymmetries that astronomers attribute to the gravitational influence of planets embedded within or near the disk. At least 2 planets have been directly imaged in the Beta Pictoris system, confirming that the disk's structure is shaped by planetary gravity, just as the Kuiper Belt is shaped by Neptune. The star Epsilon Eridani, about 10.5 light-years from Earth, has a debris disk that extends from about 35 to 90 AU. This disk is remarkably similar in scale to our own Kuiper Belt. Its inner edge is at roughly the same distance as the Kuiper Belt's inner edge. Astronomers have proposed that one or more planets in the Epsilon Eridani system are sculpting this disk, creating the clumps and gaps that observations reveal. These debris disks around other stars show us that the Kuiper Belt is not unique to our solar system. It's a common feature of planetary systems. The process that created our belt, the formation of icy bodies in the outer reaches of a protoplanetary disk, followed by gravitational sculpting by migrating planets, appears to happen routinely around other stars. This means the Kuiper Belt is not just a local curiosity. It's an example of a universal phenomenon, a window into processes that occur across the galaxy. But studying debris disks around other stars has its limits. Those disks are light-years away. We can see their overall shape and brightness distribution, but we can't resolve individual objects within them. We can't measure the orbits of specific bodies or study their compositions up close. We can't visit them. Our own Kuiper Belt is the only debris disk we can study in detail. The only one where we can examine individual objects, measure their orbits with precision, analyze their surface compositions, and even send spacecraft to fly past them. Everything we learn about the Kuiper Belt informs our understanding of debris disks in general, and by extension, our understanding of how planetary systems throughout the galaxy form and evolve. The Vera C. Rubin Observatory, expected to begin full science operations in the coming years, will conduct the Legacy Survey of Space and Time, a 10-year survey of the sky that will dramatically increase the number of known Kuiper Belt objects. Current estimates suggest we know of a few thousand Kuiper Belt objects. The Rubin Observatory is expected to discover tens of thousands more, possibly over 40,000, dramatically expanding our census of the belt. With a larger sample of objects, astronomers will be able to map the belt's structure in much greater detail, identifying new orbital populations, refining our models of Neptune's migration, and perhaps discovering entirely new features that current surveys have missed. Future space missions may also venture into the Kuiper Belt. New Horizons continues to fly outward through the belt, though its instruments are limited and its power supply is slowly declining. Concepts have been proposed for dedicated Kuiper Belt missions, spacecraft designed to orbit or fly past specific Kuiper Belt objects with more capable instruments than New Horizons carried. One concept that has received significant attention is a mission to orbit Pluto, entering the Pluto system and studying it in detail over an extended period rather than the brief flyby that New Horizons accomplished. Such a mission would carry advanced spectrometers to map the composition of Pluto's surface in fine detail, radar instruments to probe beneath the frozen plains, and high-resolution cameras capable of imaging features just meters across. It would study how Pluto's thin atmosphere changes as the dwarf planet moves along its elliptical orbit, expanding when closer to the Sun and collapsing when farther away. It would monitor the slow convection of Sputnik Planetia's nitrogen ice in real time, and it would give us our first thorough look at Charon's canyon systems and polar deposits. The scientific return from an orbiter would be orders of magnitude greater than what a flyby can achieve. But the challenge is time. Even with advanced propulsion, a Pluto orbiter would take 15 to 20 years to reach its target. The scientists who design the mission might retire before the spacecraft arrives. It requires a commitment that spans careers and sometimes generations. Other proposals include missions to Eris, Makemake, Haumea, or the mid-sized objects that have never been visited at all. Each such mission would take decades to reach its target, given the enormous distances involved, but the scientific payoff would be extraordinary. Every object we visit in the Kuiper Belt reveals new surprises. Pluto was far more complex than expected. Arakoth was a pristine relic that transformed our understanding of how small bodies form. The next target, whatever it is, will almost certainly surprise us again. There's also growing interest in what the Kuiper Belt can tell us about the possibility of undiscovered planets in the outer solar system. Over the past decade, astronomers have noticed that several extremely distant Kuiper Belt objects and scattered disk objects have orbits that are strangely aligned. Their orbits cluster in ways that would be statistically unlikely if they were randomly distributed. Specifically, the arguments of perihelion, the points where these objects make their closest approach to the Sun, tend to cluster in the same region of space rather than being spread randomly around the sky. Several of these distant objects also have orbital planes that are tilted in similar directions. When astronomers Konstantin Batygin and Mike Brown published the analysis of this clustering in 2016, they proposed that the most plausible explanation was a planet roughly 5 to 10 times the mass of Earth, orbiting the Sun at a distance of several hundred AU on an elongated, inclined orbit. This hypothetical world, which the media quickly dubbed Planet 9, would take somewhere between 10,000 and 20,000 Earth years to complete a single orbit around the Sun. The idea is tantalizing but deeply controversial. Some astronomers argue that the apparent clustering is real, and that Planet 9 is the best explanation. Others argue that the clustering could be an observational bias, a result of where and when telescopes happen to have pointed, rather than a genuine physical effect. The handful of extremely distant objects we've detected is small enough that statistical flukes are possible. If the clustering is real, Planet 9 would be a remarkable discovery. A new major planet in our own solar system hiding in the darkness beyond the Kuiper Belt. A world that has been orbiting the Sun for billions of years without anyone knowing it existed. If Planet 9 does not exist, then something else must explain the orbital patterns, Perhaps a combination of gravitational effects from the known giant planets, the remnant influence of a passing star in the early solar system, or mechanisms we haven't considered yet. Either way, the answer will teach us something profound about the outer solar system's architecture. Searches are ongoing, using some of the largest telescopes in the world, scanning the sky in the directions where Planet 9 would most likely appear if it exists. The Vera C. Rubin Observatory may settle the question once and for all. If Planet 9 is out there, Rubin's deep, wide-field survey stands a good chance of finding it. Let's step back now and think about what all of this means. We started with a classroom diagram, a flat, neat, compressed picture of the solar system that shows the Kuiper Belt as a thin strip of debris at the edge. And we've discovered that this picture is profoundly wrong. The Kuiper Belt is not a thin strip. It's an enormous, three-dimensional, gravitationally sculpted structure that rivals the entire planetary solar system in scale. Its classical region spans 20 astronomical units, roughly 2/3 the distance from the Sun to Neptune. Its total volume exceeds that of the space containing all the planets. Its objects range from tiny frozen pebbles to dwarf planets large enough to have atmospheres, moons, and active geology, and its structure encodes the history of Neptune's migration and the violent rearrangement of the outer solar system that occurred billions of years ago. Beyond the classical belt, the scattered disk extends the population of icy bodies to several hundred AU. Beyond the scattered disk, objects like Sedna hint at a hidden population in the vast unexplored zone stretching to thousands of AU. And beyond that, the Oort cloud, a hypothetical but almost certainly real spherical shell of trillions of icy objects, extends to 100,000 AU, nearly halfway to the nearest star. Each of these layers is vastly larger than the one before it, and each is vastly emptier. The solar system doesn't end at Neptune, it doesn't end at Pluto, it doesn't even end at the outer edge of the Kuiper Belt. It extends, in some meaningful gravitational sense, for nearly 2 light years in every direction. And yet, for most of human history, we didn't know any of this existed. Pluto wasn't discovered until 1930. The second Kuiper Belt object, 1992 QB1, wasn't found until 1992. Most of what we know about the belt's structure and population has been learned in the past 3 decades. We've gone from complete ignorance to a detailed understanding of an enormous region of the solar system in less than a human lifetime. And we're still in the early stages of exploration. Every new telescope, every new survey, every new spacecraft mission reveals more. The Kuiper Belt is a frontier that we've only just begun to map. There's something deeply humbling about all of this. We grew up thinking we understood the solar system. We memorized the planets, we learned their order, their sizes, their distances. We thought the solar system was the Sun and 8 planets, maybe 9 if you still count Pluto. And we thought it was relatively compact, a manageable thing that fit on a poster, a structure we could wrap our minds around. But the truth is far bigger and far stranger than that. The planets are just the beginning. They're the compact inner core of a much larger system. Beyond them lies the Kuiper Belt, a vast frozen wilderness of icy worlds. Beyond the belt lies the scattered disk. Beyond the scattered disk lies the Oort cloud. And the entire system, from the Sun out to the farthest wisps of the Oort cloud, spans a region of space nearly 2 light years across. In that context, the Kuiper Belt occupies a special middle ground. It's not as familiar as the planets, but it's not as remote and inaccessible as the Oort cloud. It's the zone where the known meets the unknown, where direct observation gives way to inference, where spacecraft have ventured but barely scratched the surface. It's a place where frozen relics from the birth of the solar system drift in silence, carrying secrets about how our cosmic neighborhood came to be. The next time you see that classroom diagram, the one with the planets lined up neatly and a thin ring past Neptune, remember what you've learned tonight. That thin ring is a lie. Not a malicious one, just a practical compression. a concession to the limits of paper and ink and screen size, but a lie nonetheless. The Kuiper Belt is not a footnote. It's not an afterthought. It's not a minor detail at the edge of the solar system. It is one of the largest, most scientifically important structures in our cosmic backyard. It's a vast, sparse, frozen archive that stretches across billions of miles, sculpted by the gravity of a migrating ice giant, populated by worlds ranging from tiny frozen pebbles to complex dwarf planets with mountains, glaciers, and atmospheres. It occupies more volume than all the space containing the planets combined. And it is only the innermost layer of an even larger system of icy bodies that extends nearly halfway to the nearest star. That is the true scale of the Kuiper Belt. Not a ring, not a band, not a strip. An immense, three-dimensional wilderness of frozen worlds, dwarfing the familiar solar system that most people think of when they picture our place in space. The planets are just the beginning. The Kuiper Belt is where the solar system reveals its true size. And the most remarkable thing of all might be this. We're the first generation of humans to know about it. For all of human history, every civilization, every culture, every astronomer who ever looked up at the night sky, none of them knew this region existed. It took until the end of the 20th century for us to discover the first Kuiper Belt object beyond Pluto. It took until the 21st century for us to send a spacecraft there and see one of these frozen worlds up close. Everything we know about the Kuiper Belt, its scale, its structure, its populations, its history, all of it has been learned within living memory. You are among the first humans ever to understand what lies beyond Neptune. You're among the first to grasp how enormous and how empty and how structured the Kuiper Belt really is. This knowledge is new. It's still being refined. There are certainly surprises waiting out there in the frozen darkness that we haven't discovered yet. But what we already know is enough to fundamentally change how you see the solar system. It's not a compact little family of planets orbiting close to a star. It's a vast structure, most of which is cold, dark, and far from the sun. The planets are the bright, warm, central core. The Kuiper Belt is the enormous frozen wilderness that surrounds them. And the Oort cloud is the even more enormous void that surrounds that. Layer after layer, each one bigger, each one emptier, each one more remote and more mysterious than the last. That is our solar system, far bigger, far stranger, and far more wonderful than any poster ever showed you. So the next time you look up at the night sky, past the moon, past the planets, out into the dark spaces between the stars, remember that just beyond the farthest planet lies an immense frontier of frozen worlds. A region so vast that light takes hours to cross it. A place where the sun is just a bright star in a black sky, and where ancient ice drifts in orbits that take centuries to complete. The Kuiper Belt, hiding in plain sight, compressed into a thin line on every diagram, but in reality, one of the grandest structures in our solar system. It was there all along. We just couldn't see it for what it was until we finally learned to look. Thank you for joining me on this journey to the outer solar system. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. The Kuiper Belt is vast, silent, and ancient, and we are only beginning to understand it. Good night, and may you never look at that solar system poster the same way again.